Hello everyone, and thank you for joining us for today's Surface Measurement Systems webinar being hosted as part of our one-week online festival of inverse gas chromatography, IGC SEA Week. Thank you everyone for joining us today, and I hope you have enjoyed the other educational session and research resources we've been releasing throughout IGC SEA Week. Today, we'll be exploring the topic new IGC application spaces for high temperature measurement, and we're very lucky to have with us Dr. Annette Condor, who is Surface Measurement Systems lead specialist on inverse gas chromatography. As with all of our educational events, you will have an opportunity to have any questions asked and answered by Annette Condor in the live Q&A session at the end of her presentation. To take part in this, there are two very simple ways. You can either submit your questions in writing in the questions panel, and then I will ask Annette the question when we come to the Q&A session. Or if you have a bit of an extended question or a two-part, three-part question you'd like to ask yourself, please just select the correct icon to raise your hand when they come to the Q&A, and I will let you know when you can unmute your microphone and engage Dr. Condor directly with your question. So before I pass over, I just thought I'd give you all a quick background on for the presenter today. So Annette Condor is the IGC SEA Product Manager and Product Specialist of Surface Measurement Systems. Since 2005, Annette has been working on gas chromatographic techniques, and she studied chemical engineering at the University of Pannonia, Hungary, where she received her master's in chemical engineering accredited by the British Institution of Chemical Engineers, and she received a PhD in chemistry and environmental science. She received a PhD in chemistry and environmental science. She published several research works in peer-reviewed journals, collaborating with research groups from around the world. And her research interests lie in areas of surface characterization of different solid materials and improvements to the inverse gas chromatographic technique. We're very lucky to have Annette here today with us, as she really is one of the world's leading authorities on inverse gas chromatography, both the technique and its instrumentations. So without further ado, I will hand over to Dr. Condor to begin our presentation.
Hi, John, and hi, everyone. Good morning, good afternoon, whichever is the time at your location. Thank you, John, for that nice introduction. And today I will show you some applications, especially at high temperature range. And the overview of my presentation is on this slide. So first I will show you a study on zeolite, an adsorption study, and then another study where we investigated temperature effect on surface energy in case of zeolite and graphite. And then I will show you another study on diffusion coefficient, and at the end of my presentation I will show you the high temperature SEA system and a couple details of this device. The first study is an adsorption study on zeolite sample, and in this study we determined the BT aromatic hydrocarbons adsorption isotherms at different temperature on zeolite sample. The BTEX compounds are the benzene, ethylbenzene, toluene, and some silane adsorptive molecules. And the adsorbent within this study was Degussa DAYF20 hydrophobe zeolite. It was a dealuminated zeolite. The specific surface area of this zeolite is 657 meters square per gram, what we determined with a nitrogen volumetric system. And for the IGC measurements, we crushed this zeolite and then fractionated with a set of standard sieves, and then selected a specific fraction, which was from 200 to 500 microns. And we packed from this fraction into a glass column 274.2 milligram precisely. And we used a 4 milli ID column. And first, we determined the surface energy at 150 Celsius degree. And on this slide, you can see the surface energy profile and the surface energy distribution. You can see that the dispersive component of this zeolite is very uniform energetically. There's not too many difference in the dispersive energy size. Although we measured a relatively heterogeneous specific surface energy, which can be related to the inhomogeneous surface modification of this zeolite, because it was partially deilluminated, and probably this caused this significant decreases in the specific surface energy, and we measured various specific surface energy sites on this surface. After we characterized the surface, we measured those aromatic hydrocarbons adsorption isotherms at different temperatures. On this slide, you can see an example. It's an orthosilane adsorption isotherms at different temperatures. So from 170 Celsius up to 250 Celsius degree. And from the adsorption isotherms, we determine the Henry constants for all the different aromatic hydrocarbons. And we plotted the Henry constants against the temperature, but you can see on the right graph. And also, we compared the different Henry constants of the aromatic hydrocarbons with other zeolites, with other adsorbents. And on this graph, you can see the comparison in case of benzene. So you can see the in what we measured Henry constants for benzene on this zeolite is the black dots, filled dots, and there's a straight line also represent the trend of these dots. And you can see that the Henry constants of benzene on this zeolite is higher compared with other adsorbents. And see, based on the results, we can say that this zeolite has an excellent adsorption capacity for benzene. It's much better than the 4A zeolite or sepiolite, for example. This study was published in the Journal of Chromatography. So if you are interested in this study, we are happy to share this paper with you. Just let us know at the end of the presentation. On the next slides, I will show you some results on the temperature effect measurements. So we determined the temperature effect on surface energy in case of zeolite 13X and graphite, a natural graphite sample. On the first graph shows the zeolite 13X results at 300, 350, and 400 Celsius degree. At 300 and 350, the dispersive surface energy profile you can see is quite uniform. Although at 400 Celsius, it shows some degree of heterogeneity. And also what you can see that it increasing with the temperature. So the surface energy level of this zeolite is increasing with the temperature. So the temperature has an effect on the surface energetics of this zeolite 13X, which can affect the adsorption behavior and the adsorption capacity of some molecules. On this slide, you can see the natural graphite surface energetics at different temperatures, 100 and 120 Celsius. And this sample seems doesn't affected by the temperature much, so the surface energy doesn't change with the temperature. And we used a natural graphite anode powder, which was supplied by Sigma Aldrich. And there's also different types of graphite, so not just natural graphite, but there's synthetic graphite or composite graphite. All these graphite produced differently, and what is also important fact that the raw material is different. So in case of the natural graphite, the raw material is a graphite ore, and in case of the synthetic graphite, the raw material is a petroleum coke or coal. It's known that raw material and the processing way of a solid has an effect on the surface properties of the final product. And unfortunately, I can't show you data on the synthetic graphite, but I can tell that it's a completely different surface energy than the natural graphite. So you saw that the natural graphite has a quite uniform surface energy profile, and it doesn't change with the temperature. Synthetic graphite has a different energy levels due to the production process, the raw material, and some other factors as well. On the next couple slides, I will show you some diffusion coefficient data by pulse injection using IGC SES system. So we implemented into the analysis software the diffusion coefficients calculation, and for the application panel, we use this publication as a basis, which because this publication describes very well the diffusion coefficients calculation by inverse gas chromatography. And the diffusion coefficients calculation is really based on the one-Denter equation, and it's a little bit simplified because you can see the red line become almost zero. So where you can work with IGC at the linear velocity range, this component, the longitudinal diffusion component, become very, very small and zero. So this component is excluded from the one-Denter equation, but the other parameters are in there. The diffusion measurement based on the different flow rate and IGC is an appropriate tool to measure transport diffusion. Since the experiments are performed in the flowing system and under concentration gradients. And for example, in FCC process, diffusion is supported by flow and concentration gradients, the same kind of diffusion what we can measure with inverse gas chromatography. In our software, the IGC SE analysis software now has its application panel where you can directly and automatically calculate the diffusion coefficients. And the panel is looks like this. And I just show you now data when we use this application. So the two samples, they were 2 microporous catalysts. Then we measure cyclohexane and toluene at diffusion coefficients at 2 different temperatures, 250 and 300 Celsius. The carrier flow rate was varied from 5 to 32. This is so we injected the cyclohexane and toluene several times, and we use different flow rates in each case. Then we determined the diffusion coefficients and we performed 3 runs. You can see the relative standard deviation of the experiments are quite good. And here's the graphical demonstration of the results. So you can see the 2 different samples. Blue is the sample 1 and orange is the sample 2. And the 2 probe cyclohexane and toluene at 2 different temperatures. You can see that the blue blocks, so the on the sample 1, the diffusion coefficients of the 2 different probes at the 2 different temperatures doesn't change much with the temperature, but on the sample 2, the temperature has a significant effect on the diffusion coefficients in case of both probes, so in case of cyclohexane and toluene as well. So sample 2 has the surface of the sample 2 is not that stable at the different temperatures, so that's why the diffusion coefficients also changing the temperature. We presented these results and other study in this case study. What you received on Monday with the package, or you can still download that application note package. This also was in that support documents. And if you are interested in diffusion analysis, we recommend this case study, and we can share with you the method setup and all the details. So as I promised, the last couple of slides is contains the high temperature SCA details, some parameters. Same hardware with a little modification. So our high temperature SCA has a temperature range from 30 to 500 Celsius. The stability of the set point all over the temperature range is less than 0.5, and it has mass flow controllers with flow rates from 0 to 100 milliliter per minute. And we added a safety feature because 500 Celsius is quite high, so we added the safety features to the instrument. So there's an integrated warning system with, to prevent exposure to heat elements of the system. And just a little bit detailed picture about the oven. It's a schematic graph. So we collaborated with a German company to design this high temperature oven. And it has a direct column heating, which is really efficient. And it's important when you measure thermodynamic parameters, because the temperature has to be very stable along the column. And also during the whole experiment, the temperature has to be stable. So this oven has the excellent stability. It's less than 0.5 Celsius in the whole temperature range from 30 to 500. We can provide the system with different inner diameter columns. The column material can be quartz, selenized glass, or stainless steel. And again, we have also a cutoff switch for safety reasons. So here's the specs, the summary. Temperature ranges from 30 to 500. The temperature control accuracy is 0.1 Celsius, and the oven temperature control accuracy range. So at low temperature, around 30 Celsius, it's just 0.1 Celsius, the stability, but at the highest temperatures, we can get very, very good stability, is 0.5 Celsius. So along the whole range is less than 0.5. It has the system has still has an automated injection system. The flow range is quite wide, and it's stable. Also, we tested, so from 0 to 100 milliliter per minute, you can set a reference flow, and it's automatically controlled and generated during the experiment, which is important for the diffusion coefficients measurements. The temperature stability also important, but temperature stability is more important for surface energy and absorption measurements, whereas the thermodynamic parameters measured. So that's our high temperature SEA, and basically where high temperature SEA can be used. So you can use to characterize different solid surfaces. You can measure the temperature effect, and especially the temperature effect on surface properties of adsorbents, which has a strong adsorption properties. It can be used to determine processing performance, diffusion coefficients measurements, and also you can measure homogeneity studies on catalyst carbon graphite samples. So that's all I wanted to share with you today. And if you are really interested in this high temperature SEA, or if you want to measure properties at high temperature, please contact with us. We are happy to assist you. And also, if you have any questions, I'm happy to answer them. Thank you for your attention, and the floor is yours.
Thank you, Annette. That was a great presentation. Yes, we have a few questions in already. So just a quick reminder before we dive into those. If you would like to ask a question based on the presentation you just saw, or on anything IGC related, which Annette can answer, please submit these in writing in the questions panel, or raise your hand and we can come around to you to let you know when you can unmute your microphone and ask your question in person. So the first question we have is, which range in isotherms was used for the calculation of Henry's constant in the zeolite study?
Yeah, so basically we used all the measured isotherms. So at each temperature, we measured the adsorption isotherm. So from 170, I think the smallest one was 150 Celsius, and we went up to 250 Celsius. And at each temperature, we determine the Henry constant. And on this graph on the right side, you can see the Henry constant at different temperatures. So you can see it was, I think 423 was the smallest temperature, what we used in case of the benzene and the toluene. For the other solvents, for the other aromatic hydrocarbons, the smallest temperature was 170, and we went up to 250 Celsius. So the Henry constant, the Henry constant was determined at each temperatures for each adsorption isotherms.
Great, thank you. A question here. Do you have any examples related to activated carbon showing the surface energy profile?
Yeah, we measured the activated carbons, but I can't show you right now because I didn't prepare any data on activated carbon, but yeah, we do have, so we can share with you, whoever asked. So just drop us an email and then we can show you data on activated carbon.
Yeah, we'll follow up with that that question after this session, just to kind of address that query in a bit more detailed fashion. Another question here, is it possible to measure the surface area of a zeolite with the IGC technique? What's the recommended sample amount for the zeolite samples?
Yeah, it's a good question. Unfortunately, we can't measure high surface area with IGC technique due to technical limitation, due to the pulse injection. Actually, the pulse injection has its own limitations, so we can't really inject in pulse a huge amount of solvents which would saturate a surface of this zeolite, which has a quite high surface area, like almost 700 meters square per gram. We determine the maximum surface area. What we can determine with pulse injection, it's around 120 meters square per gram. That's what we can accurately determine, because in that case we have measured data points in the whole BT range. Higher surface area, it happened that was determined, but in that case just a few data points was in the BT range. So unfortunately, with pulse injection, you can't measure this high surface area, although it's possible with frontal injections, what we are working on to add to the instrument. But it's almost the same like the DVS. So with the DVS, with our other product, you can measure high surface area because there's a constant concentration of the organic vapor or water, and it helps you to saturate the surface with the probe. So at the moment, unfortunately, you can't measure, and yeah, I don't have recommendation for the mass, but yeah, we are working on it. And if you have DVS, you can use that or other technique.
A bit of an interesting question here, I think more practical side of IGC, and they ask, the column being used in the IGC SEA is a tube with different diameters, 2, 3, 4 millimeters, etc. Whereas the analytical GC, which is, they understand, is a different purpose instrument, but that uses a capillary coiled column. And they were wondering, in your opinion, if you were to use a capillary coiled column in an IGC, will it have any effect on the accuracy of the end results, as the retention may be greater than a normal column?
Yeah, it's a interesting question, and yeah, it's a good one as well. So in case of analytical GC, the columns, capillary columns, are quite long, and they that column contains a lot of solid, relatively a lot, because along the column the different compounds need to be separated, and basically there's a lot of surface also in that capillary column, for this reason, to help the separation of the different compounds. So at the end you will detect them separately. In case of IGC measurements, when you investigate your solid surface, when basically your which is in the column is your sample of interest, it's not necessary to have that huge surface or that big surface area, and that's why we use a different type of columns. Even though when during my PhD studies we used a U-shaped column for IGC measurements, we haven't had to pack fully those columns. So like in case of this zeolite, we also just use 274 milligram So I don't think that it would be useful or necessary, because that would increase the measurement time, and also it's not suitable, the capillary column, to our IGC, but maybe other home build IGCs you could, but I don't think that is it's a practical thing.
Thank you. Another question here, and they ask, the experiment with high temperature is above the boiling point of some probe molecules like cyclohexane, toluene. Does this cause any issues when it comes to vapor injection?
No, we inject everything in a vapor phase. So like IGC SEA has a vapor phase injections, like a head phase injection for analytical GC. So we already inject everything in vapor phase. So the injector port, it doesn't affect, or this doesn't affect the injections. So yeah, in this case now.
Great. Another kind of a practical question about the high temperature IGC, as someone asks, if they were using the original IGC SEA with a 150 temperature range, is it possible to upgrade that system to a 500 temperature range without changing the whole system?
We are working on this to solve this upgrade. I recommend this person to contact with the local sales or our direct sales people. Yeah, we can negotiate this. Yeah, at the moment we don't really offer, but because it has mainly the same base. But yeah, it's under discussion. So let's contact with our direct sales people, and then we can discuss. Okay, but actually the instrument has to be shipped back, definitely. So maybe the cost wise it wouldn't really burst to them, because it would be like it's buying the same instrument. So I don't know. Yeah, contact with the salespeople and then we can negotiate, or we can discuss.
Great. And then this question here, what types of tube are suitable for measurement with this technique? Is it I think they're inquiring especially is, does the material have an effect? Does it have to be a specific type of material you're using?
So for high temperatures, so if the temperature is above 200, we recommend the quartz column, which is stable at high temperature and won't break like the glass. So we recommend the quartz column or the stainless steel tube. We tested these columns, so there's no any effects. I mean, with the probes or anything. So you can use any of these columns.
Okay,
Maybe it's just me, but you were breaking up, so I couldn't hear the last question.
Sorry, no,
there was a question.
No, I just muted while I was pulling up the question.
Okay.
So they've asked, apart from the common organic vapor, is it possible to use some other vapors, such as fragrances like pinene or limonene? Is there any limitation about the minimum vapor pressure when doing this?
There's a slight limitation, but I used limonene in the IGC, and I use eucalyptol or linalool, some fragrances, because during my PhD, I was working with fragrances and flavor compounds, and then we purchased the IGC SEA, so we did a couple experiments using IGC SEA system. And then we could really measure fragrances and flavors. Yeah, contact with us, and we can assist, we can help you, because you need a couple of parameters to enter into the database, and yeah, we can help you with that, but it's possible. And what is the benefits really with IGC? You can inject much smaller concentrations with IGC SCA due to the vapor phase injection than what we could inject with a normal syringe GC system, so IGC system, when we use the syringe, because the smallest syringe for automated injections, I think it's a 5 microliter. I think it's for Agilent, but that with vapor phase injection, you can inject much more smaller amount, smaller moles than what basically you can inject in a liquid phase with the 5 microliter syringe. So yeah, you can do fragrances, flavors. You can do so many, yeah, nasty stuff.
Great, thank you. We have another question, but I think this is one that I can cover for the audience. The question is asking if there's any other resources that they can consult to learn more about the technique. And I can say, yes, there are plenty of techniques. Our website gives a detailed explanation and exploration of this technique. And there is also a huge library of application notes available for download on our website in the download section. And furthermore, we have a YouTube page which has both introductory videos describing the technique, as well as a range of webinars and workshops going into everything from the basics of the technique and introduction to the technique to involved applications of the technique in different markets. And then furthermore to this, our members of our team are always more than happy to schedule a call or have a meeting with you to kind of explain the technique in a bit more detail and go through your kind of thoughts and questions about the method. So yeah, so that, I hope that answers your question.
Yes, yeah, I confirm. Yeah, we are always happy to arrange a meeting, discuss specific questions, applications. So we have a quite big scientific team with a lot of experts. So yeah, just contact with us if you can't find that specific answer on our websites or on our documents.
And another question that's just come in, Annette. They ask, is it possible to measure MOF materials with IGC? And if the preheating temperature will affect the structure or stability of the MOF, is it going to change the surface energy as well?
It's a great question, and the answer yes and no. So in more detail, so yes, you can measure MOFs. There's a customer who measures MOFs, and it's possible. They published a couple of papers on MOFs. And I don't know, maybe they already investigated this temperature, the preconditioning effect, the pretreatment temperature effect. I don't know, is there any studies out there? I haven't done yet so far this kind of study. Yeah, but it's a very interesting yeah, application or study which could be done on this instrument. And, a very informative kind of study, because MOFs are really, yeah, at the moment there's a huge interest on MOFs materials. But yeah, you can measure with IGC, of course. And we can share the link of that publications which studied MOFs material. So yeah, contact with us and then we can, yeah, share more information on this.
Well, I think that's all the questions we have for now. We're coming up nearly to the end of our time, so I think we'll leave it there. So once again, Annette, a huge thank you for being with us today, for not only for answering all the questions and giving us a brilliant insight into this new product we're kind of working on, but also just for being kind of the central force in organising IGC Week to kind of promote this technique for the scientific community.
Oh, thank you, John. Thank you. And also thank you for a huge amount of help on this. And thank you for the yeah, the audience. Without you, without the community, we couldn't arrange this. We could just
Thank you so much
discuss
for
with
that.
each other. Yeah, thank
Yeah.
you. Thank you for taking time, and thank you for your attention again.
So yeah, and from myself, a thank you again to our audience and to our speaker. And of course, IGC SEA week is not yet over. We have one final and possibly our most exciting release coming tomorrow. This is our IGC Zorkian Science Directory 2019 edition for IGC. Now, if you're ever in need of historical references and studies to inform new research or to build a hypothesis, or for whatever reason you may need to look back and acquire industry-sorted and application-sorted studies in the IGC space, we are slowly working our way through the years to give you a catalogued glossary of all studies published related to inverse gas chromatography and the IGC SEA. And the 2019 edition for the IGC will be released tomorrow. So please keep a lookout in your inbox and you'll be sent a link to download this free of charge. So keep an eye out for that around lunchtime tomorrow. So that brings us to the end of today's session. I'd love to say thank you again to everyone who attended and for supporting both this session, the IGC week event, and for IGC and the IGC technique in general. So once again, thank you to Annette and our attendees, and wherever you are, have an enjoyable remainder of your day. Thank you.